me show you how to be a good breezy and change your predictions.
Yingzhen, let's start with you. I'd love to talk about what you're currently doing right now. So if you could maybe take an example of what you're currently working on, and maybe tell us about the challenges you're facing, how you're addressing them, and where you're hoping to take the project.
Yeah, so as I said, right, so we've been doing quite a lot of different things about applying, Bayesian computation or probabilistic inference techniques to various generative modeling settings. So maybe one thing that is relevant here is about, quantifying uncertainty in neural networks. So one thing that we can see right now here is we have very amazing chatbots and other kind of generative AI models around us, like ChatGPT, Gemini, or Claude, right? So those are giant neural networks trained on tremendous amount of data, right? So that's how they gain their sort of like a power of doing all these intelligent things. So then the interesting question here is, do we still need to quantify uncertainty, right? Well, in this big model, right? So that is actually a very interesting question, because around maybe 10 years ago, when the neural networks are bigger than traditional statistical model, but still not too big at this scale, right? We can still ask the question about, okay, if I train a neural network on, some image data set, should I also quantify uncertainty based on, okay, the image that we haven't seen or some other edge cases, right? So that's how this interesting field of Bayesian deep learning got popular again, and people, including myself, have research on various Bayesian computation methods, efficient computation methods, on how to train what is called Bayesian neural networks, where you can think about it as a neural network, but you treat the weights of the neural network as a random variable, and then you put a prior distribution over it, and you do the Bayesian treatment to get the posterior, right? So there has been a lot of development there, but going back to nowadays, given that this model right now we have for language model is so big, and presumably they have already trained on the entire web of the data point, you might thought that, okay, there might not be any leftover unseen data point that might not be interesting at all, right, in terms of uncertainty communication, and there has been computational challenges of doing that. So, but now people also start to think about, okay, can we do this kind of Bayesian techniques in the fine-tuning procedure, where you're going to fine-tune your pre-training language model to some, say, domain-specific data sets, or whether you can even do this kind of uncertainty communication when you're just trying to prompt your language model with some instructions, whether the language model can understand. There might be some uncertainty or some ambiguity beyond the prompt that you provide to the language model. So this actually opened up some new avenues for Bayesian methods applied there, and we are actively researching on that domain.
Yeah, that's absolutely fascinating. And Mélodie, that makes me think a bit about what you said you're working on in your introduction. So how wrong am I to think that? How related is your work?
Yeah, it's very related. So I'm not working on large language modeling, though, but it's very related because, as I said, I'm kind of Bayesian at heart. So for me, it's really, as I said, using machine learning tools to enhance Bayesian statistics, and of course, Bayesian neural network, as you just talked about, are really in the middle of all of this, because in Bayesian deep learning, Bayesian neural network are kind of ominous, right? So I think for me, what I'm really interested about is to be able to build Bayesian models. So when I say Bayesian models, I really mean think about it as really a Bayesian hierarchical model. So from all the connection with maybe multiple data sources, maybe multiple response, maybe layers of parameters, maybe functions and functional operators with it. Think about it as like a complex model, right? But in it, you want to be able to accommodate covariates, which are non-structured or very high dimensional. So for example, if I give you some MRI data and some genomics data of a patient, can you predict the 5-year survival? And so I'm really interested into being able to do this, but with uncertainty quantification, and not like an ad hoc uncertainty quantification, but actually a real Bayesian inference and a real uncertainty quantification that is both aleatoric and epistemic. So that's what I'm interested in. And you mentioned about maybe a recent project. Just to give an example, is with a collaborator at Imperial and the University of Copenhagen. We recently released a preprint, which is about deep survival analysis. So this is really a survival analysis model, but in it you have a neural network that models your hazard. And this allows you, again, if you had my MRI example, to use a neural network which has the inductive bias that you want, because there have been a lot of empirical studies that have shown that, say, a convolutional neural network could have a correct inductive biases. So you can leverage this rather than using another prior that you don't really know how it informs what. So this is what we've developed, and I think for me the three main characteristics that I would like to, what I aim to go to is really having models that are both principled, so you can have a prior specification from expert knowledge, and this is really hard to do in deep learning, as you just mentioned. You mentioned the prior and the weights, but the problem in deep learning is that the expectation of a neural network is not known in closed form, given that the weights are stochastic. And this is exceptionally complicated, because then you cannot resonate in terms of, I'm going to place a prior because I know that my expectation is going to be this value, because you cannot have the expectation. So being able to specify a prior is very challenging and one of my interests. Then, of course, being able to do inference, which is not easy when you have big data. And lastly, theoretical guarantees. So we might talk more a bit about the tools that are available, but for now, there have not been theoretical guarantees that an uncertainty of in neural network were quantified were actually the uncertainty of the true posterior.
Okay, yeah. Thanks, Mélodie. If indeed, lots of questions for you in a few more minutes. But first, ethics. When we were talking before the show, like Yingzhen and Mélodie were telling me, well, basically what we do is kind of like trying to get Bayes into machine learning, and since you're French, you're contrarian, and so you said, no, I do the contrary. I do machine learning for Bayes. So of course I'm summarizing here, but yeah, can you maybe tell us what that means for you? What would that mean to try and use machine learning tools to include that into Bayesian models?
Sure. So I guess my first contrarian point is that I'm actually Belgian, not French, which is but so this is the most important misunderstanding of this.
Yeah, I mean, I don't know. That was very French of me. So that was on point.
You have a strong prior.
Yeah, I guess we did discuss this before the start of the podcast, but actually, I think I resonate with a lot of things that Mélodie just said. So for me, the kind of difficulty with being Bayesian about machine learning is that there's a lot of quantities that it's actually really hard to put priors on, right? So we've talked already about the weights of neural networks. This might be something that's well accepted in the machine learning community. If you go to a statistics department and you tell them that I'm going to put, priors on weights of something very complicated, people are going to start to worry, basically. And so to me, the advantages of Bayesian deep learning, and maybe Yingzhen will disagree with this, and maybe this will be the kind of topic of this panel, but basically having stochasticity on some weights of a neural network provides something else. It doesn't provide uncertainty in the same way that, you would typically expect from a Bayesian model. So if I have a, important scientific problem with an important quantity of interest that I want to recover, it's kind of a lot more clear what you should do, right? You place a prior and you're going to try to update that with data. Here, actually, in the weights of a neural network, no one cares about the weights of a neural network, right? So really, it's a way of kind of providing stochasticity, and that might have some advantages, and I'm sure Yingzhen will kind of tell us a lot about that much better than I could. But it's really quite a different task. So I guess what I meant earlier when I said I'm kind of more into kind of using machine learning for Bayes is more that the sort of thing that Mélodie was talking about. So, like maybe you have a very complex model, and actually, part of that model is kind of you want to have some more flexibility in there, and then maybe using some sort of machine learning method in that part of the model kind of makes sense. But I'm still very interested in kind of the sort of techniques that Bayes was originally for, or at least that for many years statisticians have focused on, which is kind of like caring about uncertainty of parameters that are kind of meaningful in some way, in some kind of fundamental way. So just to give some examples, so one topic that I've worked on is simulation-based inference. So that's one of the areas where I work on now. So they're really kind of, where the field of machine learning has brought a lot has been in giving very flexible conditional density estimators, essentially, that can act as essentially surrogate for a likelihood which might not be available to then allow us to do Bayes. And, here all we need is really something that, a very flexible model that can essentially approximate any density. But we're not actually using, being Bayesian about the parameters of that model. We just use this as a surrogate to then be able to do Bayesian inference about certain parameters we care about. And to me, this is like, obviously, I don't need to kind of say much about how much machine learning has changed things in recent years, but clearly, there's a lot of things that statisticians could take, and I think it's, slowly starting to happen. So, only a few years ago, I don't think statisticians would have even considered doing something like this, whereas now it's becoming much more accepted. And I think that's the sort of thing that we're going to see more and more of in the future.
And how, like here, for instance, in this case, if people wanted to do simulation-based inference, what would you recommend? What tools would you recommend someone look into to actually do it implement it in their research or project?
So you're talking about more like programming tools?
Yeah, exactly. Yeah.
Okay.
Or
So,
open source software, stuff like that.
yeah. So I mean, there's a bunch of packages, and I'm not gonna take one suggestion.
Oh yeah, you can name a bunch. And
I don't want to get in trouble with.
That's fine. You can name a bunch, and then we'll add them to the show notes of this episode.
Yeah, so
but I know people interested in that. They usually go to the show notes and then try to see what would fit more their project.
Yeah, so there's a bunch of packages that people use. There's the SBI package, there's Bayesflow. I have to admit that usually I leave my PhD student to do a lot of that. So I'm not the best qualified to actually do this or talk about this. But yeah, so there's a bunch of different tools that exist out there. And I think, that's also partly why it's being picked up a lot. So actually, if I look at, the problem of simulation-based inference, so maybe I should have explained a bit more what that is. So it's basically when you're trying to do, let's say, Bayesian inference, since we're in this podcast. So you're trying to do Bayesian inference, but your model, you don't have a very good handle on it. So what you'd normally need to do Bayesian inference is a prior and a likelihood. And you might have a very good prior, but maybe your likelihood is actually very hard to write down in closed form. You cannot evaluate it. And so you cannot do Bayes as you would typically do. And so there's been, many methods that have been proposed in the literature. One of them is called approximate Bayesian computation, and that's been around for the last 20 years. And actually, very recently, these new methods that I've just talked about came in. And, the only reason that statisticians are now paying attention is actually because a lot of the practitioners actually use these kind of more machine learning methods there, and they really like them, right? So, for example, I've recently started collaborating with a cosmologist at UCL, and when we first started talking about the problems that he's trying to work on, which relate to kind of dark energy, when I suggested he use some ABC method, he really kind of just laughed at me, basically. And for him, like the advantage of these newer methods is just such that he wouldn't even consider going back. And so I think now kind of statisticians are catching up. And part of the reason that he's really into this is because there is lots of software out there that's kind of allowing that. I don't want to say that there's no software for ABC. There is also, but I think part of the reason has been that, really.
Yeah. I mean, and that's why I always ask these question based. Like, I'm myself much more of a practitioner than a theoretician, so it's always like, and that's also the way I learn. Usually, it's just like going to the website of the package or else reading the tutorials, trying the code for myself, reading the code, and I guess that's also how a lot of people use these tools because they need to use that in their projects. So having an open source software somewhere that helps you to do that is very important. So yeah, we'll definitely link to a bunch of those in the show notes. If you guys want to hear more about simulation-based inference, we have a bunch of episodes already on that. So you go to the website, and we have a keyword tool. You just look for that, and you'll see a bunch of episodes. Yingzhen, yeah, I'm actually curious. Talking about tools, the kind of problems you were talking about. How would people do that right now? Is that even something that's possible to do? Because I remember I had Vincent Fortwin on the show a few months ago, and he works a lot in Bayesian deep learning. And I asked him this question, like, what would people do if they wanted to do some Bayesian deep learning in their project? He was making the point that this is still a very active area of research, so there is no go-to tool to do that. That if you want to do the classic deep learning, it's actually super easy, especially in Python. You just fire a PyTorch or something like that, and that's super easy. But the probabilistic deep learning part is still challenging and can be hard. So yeah, I'm curious. Now we're a few months later. There is a lot of progress going on in that field. So I'm curious how you see that and what you would recommend people do.
So that's an interesting question. I think indeed in the machine learning field, right, when we do the research and trying to, implement new methods, we go to basically these, tools like a PyTorch or JAX or like even TensorFlow, but they are like these, tools that are specifically designed for just the neural network research, right? They are not designed for saying, okay, we do probability inference, right? I think there are some interesting problem right now in terms of why we haven't got very good tools. I mean, so if you look at the usual probability programming tools like Stan or like Turing or some others, right? So they are actually quite good in terms of like they have a more or less preferred inference engine. For example, like I think Stan usually use HMC, and there are some other programming languages use some other tools. But in deep learning, I don't think there are, especially in Bayesian deep learning, I don't think there is a agreed inference method. Pretty much because the neural network, Bayesian neural network procedure is also very difficult to compute, right? So people are still trying to figure out whether I should do Laplace approximation or whether I should do inference of what sense, right? And whether I should do stochastic gradient MCMC. So there is no sort of like unified agreed tool. And also, it's just, the difficulty of training Bayesian neural networks also, intertwined with the difficulty of training neural networks itself. Because at the end of the day, Bayesian deep learning methods are still using this idea of gradient descent, optimization with stochastic gradient descent as a major tool to perform the inference. So it's unclear to us whether we already have a very robust computational tools that we can agree on and then build packages on that. I mean, that said, there has been efforts, right, trying to make a wrapping package around Bayesian deep learning and just let users to use it like how people use Stan, right? So I think there has been some development for trying to do a Laplace approximation with Bayesian neural networks. That's Alex Immer and also his colleagues from on ETH. Back in my time at Microsoft, right? So I also try to make a little tool that tries to do a various different version of Bayesian inference. So that definitely works for me, right? But that wasn't flexible enough to support the general applications. So yeah. Nowadays, if you look at applying these things to, let's say, language model, either fine tuning or like in context learning prompting, right? Then another challenge is to adapt Bayesian methods to the underlying language model that you're going to use. And for different open source language model, they might have slightly different configurations, which also means that your Bayesian computation methods also need to adjust to that. Otherwise, you won't be able to get very good results. So that also raised another challenge in terms of having a unified software for Bayesian deep learning.